All right, so let's talk about applications of exponentials. This is 7-5. Please take down your essential question. What does compounding mean, and when is compounded interest beneficial to me? This is nice because we actually start talking about money, how money grows. We all like more money, so let's see how it grows in your bank account or if you've got some investments. So pause the video, take down your EQ, and let's continue. So growth and decay formulas, the functions of these all look the same. Just like we talked about last time, f of x equals b to the x. We can tell it's growth if the absolute value of the base is greater than 1. It's decay if our base is a fraction, some number less than 1. And so what we think about, for the most part, we're going to look at right now simple growth or decay, simple interest. And so the growth could be the balance in a bank account, a population of some bacteria in a little petri dish, or some other quantity. And we're going to say it grows or decays a specific percentage over a set amount of time. So this is most often seen with APR. You hear about that for cars. When you take out a loan, you get some interest, or maybe it's interest in your bank account, APR. After a year, you get some interest on the amount you had in there. Boom, your money goes up. Another year passes, boom, your money goes up by another percentage. Another year passes, boom, your money goes up by another percentage. Okay, so let's see how that mathematically works. We have two formulas, growth and decay. First one, growth, is A equals P times 1 plus R to the T power, where A is your balance or your accumulated amount. How much total is in your bank account, right? P is principal, the original amount. So there's some money sitting in there, and it's going to have some kind of R, interest rate of growth. A certain amount of time passes, and that interest rate kicks in, and you'll get a new value, A, a new balance, an accumulated amount. Your principal plus that interest, okay? Now, time is defined by the units of the, or is defined in the problem. Could be years, could be months, could be days, could be hours, minutes, seconds, whatever, okay? Now, decay, the only real difference with decay functions is we have 1 minus R to the T, so we're taking away that rate. We're making things smaller. It's getting smaller, not getting bigger. Okay? So let's look at an example. Imagine you've got a $1,000 investment that grows 10% each year. Well, what's the balance after 10 years? So first thing we want to do is make sure we recognize this is a growth problem. For growth problems, we are going to use A equals P times 1 plus R to the T. A is going to be our accumulated amount. We don't know what that is. That's what we want to find. The principal amount, how much we originally had in, is $1,000. It's going to grow by a percentage rate. R is almost always going to be a percentage rate, so that's easy to identify in your problem. We're going to write it as a decimal, 0.10. And then what's the balance after 10 years? So that tells us our time. Plug everything into that formula. A equals 1,000 times 1 plus 0.10 to the T power, and T is 10. So you can plug this into your calculator, 1,000 times 1.1 to the 10th. That's going to leave us, after 10 years, our account grew to $2,593.74. Take a minute to plug that in your calculator and just verify I'm being correct. But isn't that pretty sweet? You're not doing anything, but your bank account just more than doubled in size. You gained almost $1,600. I would take that in a heartbeat. Okay, let's take a look at another example. A room contains 100 liters of carbon monoxide, which is a potentially deadly gas. Now, an air purifier turns on every 20 minutes to reduce this amount by 5%. How much is left after 3 hours? So let's see what we have here. The thing I recognize is I'm reducing, so that makes it a decay problem, which means I'm going to use the same formula, except instead of adding 1, I'm going to adding R, I'm going to subtract R. So how much do I have to begin with of this carbon monoxide? 100 liters. What's my rate that it goes down? 5% or 0.05. Now here's where we get a little bit tricky. T. After 3 hours. But how often are we compounding here or decaying? We are doing this every 20 minutes for 3 hours. Which means 3 times every hour. Three times over the course of 3 hours. Each hour we will end up with a total of 9 times we are decreasing or decaying the amount of carbon monoxide. So that means T is going to be 9. Let's plug everything in. P was 100. 1 minus 0.05 to the 9th power, which is 100 times 0.95 to the 9th power. Plug that in, and you'll find that we have 63.025 liters left of carbon monoxide after 3 hours. Okay? So far, I don't really think this is too bad. Again, it's just plugging into some formulas. The hardest part is really identifying what each part is. So that's what's going to take some practice. Now, compounding interest. This is when interest grows with the investment. So it's not just once a year, but it could be happening more than once a year. Okay? And not only that, but it's not just your principal that's getting interest. Any interest you make, that's getting interest as well. So we have a new formula, A equals P times 1 plus R over N to the T times N power, where N is the number of compounds. So we are going to have an investment earning 5% annually. So it's a growth problem, right? And we have P 100 times 1 plus 0.05 for my interest rate divided by N. Well, how often is this really working out? Once. To the how many times a year is this going to happen? Just one time, just 1 year. So really we're at 100 times 0.05, which is $105. Not a ton in there. Let's see if it's compounded monthly. So this was just normal simple interest. So let's look and see what happens if we do it a little more frequently. 100 times 1 plus 0.05, but we're going to do that monthly, 12 times a year, 12 months a year. We raise that up to the T times N, 1 year times 12 months. And after the course of a year, you will have made just a teeny little bit more. So really what this is depending on mostly is your principal to begin with and how often you're compounding. The more times you compound, the more money you're going to get in interest. But you also need to start with something big. Okay, let's take a look at another example. Find the balance of an account earning 10% APR if $10,000 is invested for 10 years. Okay, so simple interest, just like what we did before. A is going to equal my principal, $10,000, times 1 plus 0.10 to the 10th power. That makes some pretty sweet coin, $25,937.42 after you plug that into the calculator. Let's see what happens if we compound it monthly. How much more are we going to get? Same idea. A is going to equal 10,000 times 1 plus my interest rate divided by the number of times I'm compounding per year, 12. Raised up 12 times each year for 10 years. So pause for a second, punch all this into the calculator and see what you get. Did you get $27,000? $27,000, $27,070.41. So just by compounding monthly, we actually increased our investment by over $1,000. What happens if we compound daily? What do we get? So we have 10,000 times 1 plus my interest rate, 10%. Now, if I'm compounding daily, how many times is that happening in a year? 365. Disregarding the occasional leap year, we're going to forget about that for just right now. But then we take it that it's happening 365 times a year for 10 years. Go ahead and punch that in your calculator. Pause video for a second. What do you get? Did you get $27,179.10? And that is compound interest. Okay, so at this point, rewatch any examples you need to. Take a look at the assignment that I have for you. Have a great day.